Okay, we're now going to be moving on with our discussion on vectors and extend everything that we've done so far, which has been in 2D vectors, into the realm of 3 dimensions, and we'll be talking about 3D vectors. Okay, so just to help you understand what 3D vectors would look like, here's what we've done so far, right? We've done 2D vectors where our vectors have had 2 components, an x component and a y component, and we've seen that it looks like this in component form, where the first number is the x component and the second number is the y component. When we extend this and go into 3D vectors, our plane slightly changes. So whereas usually our x value goes in the direction to the right, now our x direction comes out of the page. It sort of comes out of the page there like this. And our y direction, or our y-axis, whereas before it was going up in our 2D vectors, now it's going to the right. Okay? And from that plane, you have to think of this sort of like a tabletop here. From the top of the table, we see this vertical new axis come out, and that's our z-axis. Okay? Now, this isn't the case. This isn't the orientation of these 3 axes for all situations, but for the purposes of this course, we'll be using this orientation. Okay, and you'll also see this orientation in the DP. So let's see what a 3D vector looks like. Basically, it's going to have 3 numbers that describe where the vector is and which direction it's pointing in. One that tells me the direction in the x direction, so this first component, and then the second number, just like we do in our 2D, describes the direction in the second direction, which is the y-axis, in the y direction. And then our third number down here represents the direction that it would go in the z direction. Okay, and then that would be my final destination point. Okay, so that would be my final destination point. So I would draw a line from my origin to the destination point, and that then would be my vector. Okay, now this is obviously talking about a vector that goes from 0 to another point. Okay, remember we can move vectors around any way we want as long as we don't stretch them or tilt them. The same thing applies when we talk about vectors in 3D. We can move these anywhere we want in the space, but we cannot we cannot point them in another direction or stretch their length or shorten their length. Okay, or else we would have a different vector. Okay, so that's what a 3D vector would look like in component form. And the nice thing is that the rules for 3D vectors stay exactly the same as they would for 2D vectors. Okay, so let's look at what those rules are. Okay, we started out by talking about how to find a vector between 2 points. Well, the same thing applies for 3D vectors. Okay, if I'm going from the origin to another point, really I have from 0, 0, 0, 0 to A1, A2, A3. Remember we say it's the tip minus the tail, so it's going to be the destination point coordinates, which would be A1, A2, A3, minus the tail coordinates, which would be 0, 0, 0, and we would end up with this. Okay. We could extend this to anywhere in space where we have the vector between any 2 points in space. They do not have to necessarily be, or b does not necessarily have to be at 0. Okay, and just like we did in the previous, when we were finding the vectors between 2 points where one was the origin, we do the same thing. The only thing that changes really is now we say instead of we could describe the vector AB as the vector OB minus OA. Alright, and we've done this before. I'm just giving this to you in a new context and explaining why a little bit more, why we always take B, the coordinates of the B, and subtract it from the coordinates of the A. Okay, what we're doing is we're really doing, if I were to draw 2 vectors coming out of the origin, I would have OB and OA, and then if I wanted to find from A to B, the vector from A to B, I could describe this vector as minus OA plus OB. Okay, minus OA plus OB, and this is why we do the tip coordinates minus the tail coordinates. Okay, so it's really just doing OB minus OA. We're doing OB minus OA here. So we know this already. Okay, the only thing that's new sort of is that we take the coordinates of the the z components, okay, the z components, and we subtract those to get the final z component. All right, vector equality also stays the same. Okay, if two vectors are equal, if this vector is equal to this vector, then we know that their components must be equal. A must be equal to P, B must be equal to Q, C must be equal to R. Okay. For the zero vector in 3D, we also have the zero vector described in three components. Remember that the zero vector is a vector of zero length and no direction. Okay. This is useful when we are doing algebraic operations with vectors. The magnitude of a vector, also very, very similar. The only thing that changes now is we have a plus a3 squared on the end. Normally we had just a1 squared plus a2 squared. Okay, and you would actually see this to be true if we looked at this in 3 dimensions. Okay, we could prove this in 3 dimensions, but I won't do that here. Vectors, when we're doing operations on them, okay, operations with vectors, if the vector A has these coordinates and the vector B has these coordinates, addition and subtraction rules stay the same. We are just now adding this third component down here. Scalar multiplication also stays the same. The dot product also stays the same. You've only seen up to this part right here, right? We've only seen up to this part, but now we have a new part on the end here where we're multiplying the components, the z components together. Again, the angle, finding the angle between two vectors A and B also stays the same. Okay, so everything is the same, which is great. All right, everything is the same. So really, as long as you know how to do this with 2D vectors, you should be okay with vectors in 3D. All right. All right, so in the next video, I'll show you some examples and do some applications of these.